to start off getting that Celsius to Fahrenheit, we're substituting in. So we could say 9/5, should have wrote it equals there, times Celsius plus 32. And that's how we'd get something like 0 degrees Celsius is 32 degrees Fahrenheit. You also might just know that, right? So over and over, I'm only changing my Celsius. So times 100, what do I get? 212. Swap that out for 25. What do I get? 77. Now, if you want to do the same thing here, here's where it gets challenging. Now, we would not know what the Celsius is, but we know that the Fahrenheit needs to be 104. Same function, I just know a different part, correct? So from here, if I use the same function, what I would do is I would subtract 32 from 104. So 104 minus 32 is 72. And then I would divide by 9/5 or multiply by 5/9 to get a 40. Right? And if I were to do the other two, I'd have to do all that work 2 more times. But I propose that there's something easier. I actually would do the problem number 2 before I went after these. Let me show you why. What I would choose to do is I would take my function, f equals 9/5 c plus 32, and I would rewrite my function as the inverse. So I would subtract 32 from both sides, which is what I did, right? That leaves me with 9/5 c equals f minus 32. Then I would multiply both sides by 5/9, which is the same thing as dividing by 9/5. And the result is that Celsius would equal 5/9 times f minus 32, or the Fahrenheit minus 32. And here's why I would want that. Now, I can take my Fahrenheit and just throw my Fahrenheit into there. No solving every time. It's already solved. So, 5/9 times 50 minus 32 gives me 10 degrees. And 5/9 times 62.6 minus 32 gives me 17 degrees. And I don't have to solve every time. I can solve one time to get the inverse and then just use my new function. So what would be the benefit of having these two functions then, do you think? This one and this one, instead of just one? Why might we want to? Yeah, Lily? Yeah, back and forth, whatever you want to do. We got a function for each. Same function, just the inverse, correct? So now this function down here, this Rankine, I think I'm saying it right. This one gets a little funky. There's actually 2 equivalent equations. I personally wouldn't pump this one out. I would have multiplied both sides by 5/9 first. But to get from here to here, I'm just going to do this real quick. You would distribute. That would give you r equals 9/5 c plus 491.67. 9/5 times 273.15 is 491.67. I did this, okay? And then to isolate the variable c, I would subtract 491.67, so minus 491.67. That gives me 9/5 c equals r minus 491.67. And then I'd multiply both sides by the reciprocal 5/9. And so there's that equivalent. Oops. C equals, there's that equivalent to show that it's the inverse and it's the same. But one would be good for going from Celsius to Rankine, whatever it is. And the other would be better from going from Rankine to Celsius. Because we want flexibility. It's different tools for the tool belt, right? You can use a hammer to do a lot of different jobs, but sometimes a screwdriver is better than a hammer for a certain job, right? So, tools for the tool belt when we can make an equation into another. The one, did you guys see this in science yet? The distance equals rate times time? No? So that one's cool, like distance equals rate times time. But that means that rate equals distance divided by time. And that means time equals distance divided by rate. These are all the same thing, right? Tools for the tool belt depending on what information you're given. I think you'll do that in 7th grade. Maybe not. Our next premise we're setting up is a fancy party. You know it's fancy because the tables are hexagons. None of that rectangle table junk. None of that circular table trash. Hexagons only. Okay? So you can see the little diagram. That's how you guys set them up. Now, for some reason, though, your hexagon tables can only go in one long straight line. So that's kind of interesting. This party is extra crazy. So, you're given a function in number 1. You're going to explain what it means. You're going to give a domain and a range. Remember, you guys freak out about domain and range. Remember, domain is just all inputs. Range is all outputs. Then, you're going to make an inverse function. You're going to look at that inverse function, and you're going to explain how it changed. How did the domain change? Because in theory, if we have a function, the range on the inverse is actually the domain when we make our inverse. So you're going to compare what happens to that. All right, get after it with your table partners. So, I want to ask you to help me out with different parts of my function. The first thing I'm going to label is N is tables. Are we good with that? And S is seats. And it says that. I just like to see it right in my equation. Now, let's interpret our situation. What does 4N mean then? 4 times the number of tables, Sean.
I think that's 4 times the people at tables.
Four seats.
It's like the middle. It's for the middle
At
table.
each table. That's kind of what that means, right? And they're right here. 1, 2, 3, 4.
And then there's a side.
Okay, then what's up with that plus 2?
Because like if you have, let's say you have a big row, there's always going to be 2 points.
Yeah, 1, 2. The ends, right?
Yeah.
So that's where they're getting the total number of seats. 4 at each table plus the 2 at the ends. No matter how many tables are there, there's only 2 on the ends. We good? Everybody understands the function? Okay, so what's the domain and range for this? Well, let's look at domain first. The domain is all possible inputs. So what's the lowest number of tables you could input?
1.
1, right? And then I'm going to use X. Let's use N, because N's the input. And what's the most?
Infinite.
Yeah, theoretically infinite. You could also write that in words. We also need this here too. Whole numbers. No chainsaws at this party, okay? Only whole numbers. We can't have 1.75 tables, right?
Nope, only
Are you guys understanding that domain? Has to be whole numbers. There's no 1.2 tables. There's no 37.6884 tables. Only whole numbers. Now, outputs is a little trickier. If we do 1 table, how many people is that? 6. 2 tables? 10. 3 tables? 4 tables? So you could say arrange something like that. How we would say that in words is something like multiples of 4 plus 2. So multiples of 4 plus 2. Something like that. Because the seats available are dependent on how many tables there are, and the total number of seats are always going to be multiples of 4 plus 2. Because the 2 on the ends and the 4 at each table. We go domain and range. Do you see how domain and range are easier than what some of us are thinking about doing again? What are the inputs we can have? What are the outputs we can have? All right. So, does anybody have the inverse for me already? Any ideas what the inverse function is?
Yep.
So I'll start you off. That'll be n equals. What do you have, Ryan?
S minus 2 divided by 4.
S minus 2 divided by 4. So what this is saying is the number of tables that I need is the number of seats minus 2 divided by 4. Okay? So that's good. That's my inverse function. So in this function, my domain is S, my range is N. It switches the domain and range, right? So let's test this out. 94 people. Where's that going to go in my function? N or S? It's going in for S. So 94 minus 2 divided by 4. How many tables does that give me? 23 tables, right? And those are 23 full tables. Now where it gets a little interesting with 95 seats is I get 23 and 1/4. Can we have a 4th table? So we need 24 tables. So that's going to make an interesting distinction from our domain and range. So our range from our original, n, is now our domain. So let's look at the domain of our inverse function. How can we explain the number of tables we would need? Because it's now our number of seats, sorry. Our domain is now seats instead of tables. How would we explain the number of seats that we could have? What's the lowest number of people?
6.
One person, right? So we need our people, or S, to be greater than or equal to 1, but less than or equal to infinity, and we need whole numbers, no partial people, right? Now again, here's what we're examining. The range used to be S, right? Now our domain is S. Is our old domain the same as our new, or is our old range the same as our new domain, even though they're the same letter?
Yeah. Because no.
No, because up here, they were only full tables, right? Because our relationship was between tables and seats. Well, now seats are for people in our inverse, right? And we have full people, but we don't have to have full tables with the inverse. Kind of cool, huh? So the range, when it switches to the domain, doesn't mean it's always the same. Because in context, it changes. We have full people versus full tables. Yeah, that's kind of cool. So that's just, I kind of said that, but you can write down that reasoning, right? So like full tables versus full people. Something like that. That'd be a good little summary.
The tables.
Why would we want these two functions? Well, maybe someone shows up and says, how many people can I invite to my party? And they would say, well, this many tables seat this many people. But, so they can invite all those people. Someone else might say, hey, I have this many people. Do you have enough tables for me? Those are two different things, right? The inverse function. I'm guessing party planners have to do this. They're probably doing it and they don't even know they're doing math. How about that?